Hello and welcome to Physics 2212 Lab 4. I'm Jake Bernstein. I hope you're enjoying your break, and we'll get started. So, a brief introduction. The purpose of this lab is to analyze the variation of a bar magnet's magnetic field with distance, and by measuring this field at different points, we'll then compare our results with the theoretical predictions for both on and off axis locations. We'll use Python to simulate these models. Some key assumptions are that the bar magnet behaves as a dipole. The magnet is precisely aligned with Earth's poles. The only fields affecting the phone are those from the magnet and Earth's magnetic field. The location of the magnetometer chip within the phone is known, and the strength of the magnetic field decreases as the distance increases. And right below that are a preview of the results of this lab. So the principles that govern this experiment are the Biot-Savart law, magnetic field from a dipole, and then the distance dependence formula, all pictured on the right. So first, the Biot-Savart, as we all know, is the relationship between a steady electric current from a magnetic field. And it states that magnetic field at a given point is proportional to the current and inversely proportional to the square of the distance. And this is a key principle because we then extrapolate it and apply it to the other two key principles. Here's a procedure of what this experiment entails with the magnetometer on the phone and its alignment with both Earth's axis and the object. Again, here's the setup. Pictured there's the magnetometer on Physics Toolbox Sensor Suite. And there's the bar magnet and the ruler and the tape. Now here's some experimental data that we plugged into the Excel sheet as we recorded the magnetic field at different locations. And that rough estimate is there on the right. We applied a linear curve to measure that constant, negative 2.422, which will come up later. Later being right here. As we have the formula, the magnetic field from the bar is Kr to the n, which is then simplified there, and the figures are highlighted with the magnetic field being approximately 1.8235 measured. Now we repeated the same experiment for off-axis locations, and what we're looking for in this one is right here, the 0.183 meters off-axis from the magnet. Now we have our experimental results, and I coded on Python a computational model. I'll let you go through that right there using this definition of the dipole given a mu and a r distance from the magnet. We then calculate the magnetic field, which is right there, that we got from our experiment. Now this is just iterating through, plugging in another value that we derived experimentally and approaching the magnetic field 45 degrees from the magnet. I'll let you go through that code. And then finally we have our visualization at the very end with an important vector. I think the magnitude of this vector is something like 1.66 times 10 to the negative 5. So there we have it. Now, there was a significant variance between the simulated model and the experimental, just because of the presence of other magnetic fields, some inaccuracy with the magnetometer, maybe some visual measurement areas, meaning that estimating distances or aligning by eye is a little imprecise. We have some accidental movements, and then initial alignment issues failing to zero the magnetic field. And conclusively, to address the two what-if questions, if the meter stick is positioned at an intermediate angle Earth's magnetic field will interact with the barred magnet's field asymmetrically, causing variance in the measured values. And then placing two identical magnets end to end would increase the total magnetic field strength, and this in turn would lead to higher readings at all measured points. So thank you very much. That's the end of my presentation. I hope you enjoyed.